At first glance, a plasma gasification plant seems like something out of science fiction. A monolithic chamber humming with energy, arcs of blue light flickering behind armored glass. Yet inside that chamber, the real miracle isn't only the plasma. It's the chemistry that follows. Every flash of light, every wisp of vapor, hides a deeper story. The creation of Syngas, the invisible bridge between waste and green hydrogen. It is a process so fundamental and yet so overlooked that it quietly determines the future of circular energy. The journey begins with chaos. Municipal solid waste arrives from across the city. Food scraps, plastics, old paper, even bits of fabric and rubber. This chaotic mixture is pre-treated, shredded, dried, and stripped of metals before entering the reactor. Once inside, it meets a jet of plasma hotter than any natural flame on Earth. Temperatures exceed 10,000 degrees Celsius. Molecules cease to exist. Bonds between carbon and hydrogen break apart. Atoms are liberated from their structures and drift freely in a storm of charged particles. Within milliseconds, matter dissolves into a glowing plasma cloud, the raw soup of creation itself. Then the temperature begins to fall, and the magic of Syngas chemistry begins. As the gases cool below about 2,000 degrees, the scattered atoms start to reunite in entirely new combinations. Hydrogen atoms find partners. Carbon seeks oxygen. From this molecular dance emerges a new mixture of gases: hydrogen, H2, carbon monoxide, CO, a trace of methane, CH4, some carbon dioxide, CO2, and inert nitrogen. Together they form what scientists call syngas, short for synthesis gas. It is the same mixture that once powered entire cities before the age of oil, when coal gas lit the lamps of London. Today, it is being reborn in the plasma age as the intermediate step that makes green hydrogen possible. The central reaction is ancient yet elegant. Carbon from the waste reacts with water vapor according to the simple equation C plus H2O, CO plus H2. Steam strikes hot carbon, yielding a molecule of carbon monoxide and a molecule of hydrogen. But in the heart of a plasma gasifier, this reaction happens millions of times faster than in any normal furnace. The plasma's free electrons and radicals accelerate every collision. Hydrocarbons break down into their simplest parts. Tars that would clog a normal gasifier are vaporized instantly. Even stubborn polymers like polyethylene surrender to the storm. Out of this chaos, order emerges, a clean, hydrogen-rich syngas. As engineers guide the gas stream into the next stage, they introduce more steam for the water-gas shift reaction. CO plus H2O, CO2 plus H2. Here, every carbon monoxide molecule donates another hydrogen atom, increasing the hydrogen yield even further. In traditional reactors, this step requires catalysts and precise temperature control. In a plasma system, the heat is so uniform and intense that the reaction proceeds naturally, assisted by radicals such as OH and H that exist only in plasma environments. These radicals act like molecular midwives, helping new hydrogen molecules form faster than classical kinetics would predict. It is a subtle but powerful advantage, the reason plasma gasifiers routinely produce hydrogen fractions above 50 or 60%. If you could peer into the flow, you would see a swirling aurora of chemistry. Blue and gold gases twisting together, microscopic flashes where radicals collide and reform. The plasma torch may supply the heat, but Syngas chemistry supplies the transformation. It is a cascade of reactions, cracking, reforming, shifting, each one releasing a little more hydrogen, each one cleansing a little more carbon from the stream. The physics of this process is extraordinary. At such high temperatures, the gas behaves as a non-equilibrium plasma, meaning the electrons are far hotter than the heavy particles around them. These energetic electrons strike molecules directly, breaking bonds in a billionth of a second. Unlike combustion, which relies purely on thermal energy, plasma chemistry is driven by electricity itself. Every electron that leaps across the arc becomes an agent of change, creating new reaction pathways that classical chemistry cannot achieve. This electron-driven chemistry is what makes plasma gasification not merely waste management, but a new branch of energy science. Because of these high-energy collisions, the conversion efficiency rises dramatically. Hydrocarbons yield more hydrogen per unit of carbon, and the resulting syngas is almost tar-free. Researchers call this plasma-assisted reforming, a field that merges chemical engineering with quantum physics. Once the Syngas exits the plasma zone, it passes through a quench chamber, where it is cooled rapidly to lock in its composition. The quench must be almost instantaneous. If the gas cools too slowly, new compounds can form that reduce hydrogen content. Engineers design nozzles that spray fine mists of water or recirculated gas to achieve cooling rates above 1,000 degrees per second. The art of quenching is as critical as the art of ignition. After cooling, the gas enters a sequence of purification systems, cyclones, scrubbers, and filters that remove particulates, metals, and acid gases. Chlorine from plastics is captured as hydrochloric acid, sulfur as clean gypsum, and the rest condensed into a harmless vitrified slag. What remains is a clear, colorless stream of syngas ready for the next transformation. Now comes the separation, the step that turns chemistry into fuel. Using pressure swing adsorption, PSA, or membrane separation, engineers isolate pure hydrogen from the mixture. The process is precise, tuned to reach 99.99% purity, the standard required for fuel cell vehicles. The leftover carbon dioxide can be captured, compressed, and reused in industry or mineralized into solid carbonates. Nothing is wasted. Even the heat leaving the system powers turbines or district heating networks. The entire process becomes a closed-loop ecosystem, a circular hydrogen economy in action. The chemistry underlying syngas production is simple, but controlling it is not. Temperature, feedstock composition, and steam-to-carbon ratio all shape the outcome. Too much steam dilutes the gas and wastes energy. Too little allows soot to form. At optimal balance, hydrogen yield reaches its peak, and the carbon footprint plummets. Modern plasma facilities use sensors and AI algorithms to monitor gas composition in real time. Each reading feeds into predictive models that adjust torch power and airflow instantly. The result is a living system, a reactor that thinks, learns, and self-corrects to sustain the ideal chemistry hour after hour. And yet what makes syngas truly special is its versatility. While hydrogen is the star, syngas can also become methanol, ammonia, synthetic fuels, or even jet fuel through catalytic synthesis. By simply adjusting the H2CO ratio, engineers can redirect its destiny, from power generation to chemical manufacturing. Plasma gasification thus becomes a universal gateway, converting waste not only into hydrogen but into an entire portfolio of clean products. In Kent, the planned hydrogen TE facility embodies this vision. By converting 100,000 tons of municipal waste per year into syngas, it expects to produce roughly 11,000 tons of hydrogen annually. The chemistry inside its reactors is the same as in a lab, but scaled a millionfold. Each day, thousands of tons of carbon and hydrogen atoms are stripped apart and reborn as energy. Every kilogram of hydrogen that leaves the plant represents matter reorganized, pollution turned into potential. But behind those numbers lies poetry. The hydrogen that emerges from syngas was once locked inside our everyday lives. The plastic cup, the pizza box, the newspaper. Plasma gasification returns that matter to its elemental origins. It is a modern echo of alchemy, turning base materials into something pure. Hydrogen, the first element of the universe, reborn from the cast-offs of civilization. The hidden chemistry of syngas also tells a broader story about balance. Every reaction has its mirror. For every molecule of hydrogen created, one molecule of carbon dioxide appears. Yet that CO2 can be captured or reused, meaning the net carbon footprint can be zero or even negative. When powered by renewable electricity, the plasma gasifier becomes a carbon-negative hydrogen factory, destroying waste, creating fuel, and removing greenhouse gases simultaneously. Few technologies on Earth can claim that triple effect. Still, challenges remain. The process demands reliable electricity, skilled operators, and steady feedstock. Variations in waste composition can shift the chemistry, requiring adaptive control. Engineers are developing plasma-resistant catalysts and ceramic liners that can survive continuous operation for months without replacement. These advances will drive down costs and make the technology scalable for cities worldwide. Beyond the reactor walls, syngas represents a philosophical shift. For 2 centuries, industrial chemistry has relied on fossil inputs: natural gas, oil, coal. Plasma gasification flips that model, proving that waste itself can be the new feedstock. The molecules we discard today can become the molecules that fuel tomorrow. Every landfill becomes a mine. Every refuse truck becomes part of an energy supply chain. Look closer, and the same chemistry appears in nature. Deep within volcanoes and hydrothermal vents, similar reactions occur. Carbon meets steam, hydrogen is born, and life-sustaining molecules emerge. Plasma gasification is humanity's controlled imitation of that natural creation, a miniature geothermal engine powered by electricity instead of tectonics. In the coming decade, as nations race to decarbonize, this hidden chemistry will step into the spotlight. Analysts forecast that global hydrogen demand will surpass 600 million tons by mid-century. Meeting that demand purely through electrolysis would require enormous amounts of fresh water and renewable power. But Syngas from waste offers another path, hydrogen that requires no new resources, only the ones we throw away. Imagine cities without landfills, where every kilogram of garbage becomes a kilogram of fuel. Imagine supply chains powered by hydrogen derived from yesterday's waste, ships sailing on synthetic fuels made from recycled carbon. At the heart of this vision lies the quiet, invisible work of Syngas chemistry, the conversion of matter into motion, of decay into renewal. Inside a plasma reactor, that chemistry unfolds every second. Steam flows. Carbon glows. Molecules split and reunite. And from their invisible choreography, a clear gas rises. Hydrogen, clean and limitless. If fire was humanity's first tool, plasma is its successor. Fire burns and ends, plasma reforms and continues. Through Syngas, we have learned to command that continuity, to take entropy itself and turn it into order. So the next time you hear the term Syngas, think not of smoke or waste, but of transformation. Think of a reactor humming quietly beneath the city, taking what we discard and returning it as the simplest, cleanest energy known. That is the secret within the chemistry, the unseen alchemy at the heart of plasma gasification. It is the bridge between past and future, between waste and worth. And in that bridge lies the proof that nothing is truly lost. Everything can be remade. The atoms that once built our refuse can now build our future. The chemistry of Syngas is the chemistry of renewal, the hidden science that makes green hydrogen from waste possible. Dive deeper into green hydrogen project development, feasibility models, and plasma gasification economics, ath2hub.greenenergy.com, your hub for tools, templates, and training in the emerging hydrogen economy.